according to you, which modern C++ features have most improved memory safety and management?
Oh, that's a huge question. The safety trend these days is very important to everyone working on the language. So we are all safety conscious these days. We have recently, with C++23 being adopted, introduced something called erroneous behavior, which makes it not undefined, but actually an error to do things such as read from an uninitialized variable. So prior to the introduction of that perspective from my friend Thomas Kuffe, I hope I pronounced his name right, the reading from a variable that you had not written to in the first place was what we call undefined behavior. So the compiler could actually do anything around your code because you broke the rules. Now we made that kind of stuff into an error. So we're encouraging compilers or the program to stop executing at that point because there's something wrong. It is better to have an actual hard error in such cases than just going on and hoping for the best, even though you just broke the rules. So things like that we changed. In terms of memory management, and I tried to make a point of that with the smart pointers section, the first thing you should do with memory management is don't do it. If you can avoid doing it, the automatic mechanisms just work fine in C++. But when you do need to allocate, deallocate, or manage exotic memory, control how your containers behave when you need memory, when you need that control, we have very good tools. So before you try resorting to manually allocating and deallocating, you can use the type system to do that for you in a sense. So if you use smart pointers and you say, well, that object there is the sole owner of the resource. It's written in my source code. Lots of bugs go away. You don't have to say who will free memory. It's that guy. He's responsible for it. It's his job. If you're in the more rare case where you have co-owners of the resource and you don't know which one will be the last to use, we have shared pointers. So you write that into your code as a type. So you remove the unasked question that programmers would get if you looked at raw pointers, which is who's responsible for that thing? How should I free it? Should I even free it? Is it my job? If it's in type system, you don't ask that question. So that removes a whole class of bugs. If you're trying to use raw array by hand, sometimes you need to. But we have those cool things like vectors that do that management for you, that grow efficiently. And when you look at how you can write that thing when you want to be efficient, you really respect the ones who actually do that job because it can get very complicated. So we don't write in the book every function of vector, but we write a few. To give you an idea of if you really want that level of performance, what do you need to worry about? And that's kind of enlightening if you've never thought about that. It's really cool. So if you use the type system to your advantage, a whole class of bugs goes away. It really helps you. So yeah, I don't know if it's a new way of thinking because containers have been there for a while, smart pointers for more than a decade, much more than that indeed, but the ones that we use today have been there since 2011. What the book will bring you is if you need to encode into your type system other memory management strategies than the default was, how can you do that? Can you customize, say, unique pointer to free your resource in a different way than just calling delete on it? Of course you can. Here's how you can do that. Here's the costs. Here's the way to do it without a cost, because my customers costs, they worry about that quite a bit. If you have different semantics, then I'm the sole owner or we're co-owners, there's a way to express that too. So we write our own smart pointers that are not the standard ones, but that have different semantics that sometimes you might need in your code. So again, if you move from a manual standpoint to something that uses type system to your advantage, your code will be safer, I think. So from a safety perspective, there's that. The other thing, of course, is exception safety. Lots of users do not use exceptions in C++. My game programmers and my embedded system programmers are of those, but a lot of people actually do. And if you have exceptions in your code, well, you need to make sure that your resources get deallocated or freed properly too. So the book, of course, goes into that. It was suggested to me to write a chapter on that, but instead what we did was use it as a common thread throughout. So all chapters worry about execution safety to make sure that the word gets across and it's clear. I hope it's a long question, a long answer, but I hope it's okay.
No. Like, please feel free to go as in depth as you feel is necessary. Actually, you've almost answered a part of what my next question was supposed to be. My next question was, what memory-related mistakes are still common in current C++ code bases, and what tools or practices help reduce these errors? So would you like to just explore this question a bit more?
Yeah, it's a beautiful question because it's an actual problem. We are, over time, reducing the number of cases where you'll get in trouble with C++. If you use C++ as C++, you have a lot less bugs than you would if you used it otherwise. Again, C is a fine language, but if you write C++, it's better to think in C++. As I said, your code would be smaller, probably faster in many ways. So the bugs we still have, the problems we still have, the main one is probably what we call dangling references. There's ways to express code in which you're referring sometimes to objects that have gone away. Lifetime is at the core, lifetime management of your objects is at the core of C++, really. Lots of things we do in C++ are tied to the way the object lifetime cycle works. We use the end of the life of our object, and we have a chapter on that in the book, to free resources. There's an idiom tied to that called RAII, resource acquisition is initialization, or responsibility acquisition is initialization, depending on who you ask. So we actually have a chapter on that because it's so characteristic of C++ to do this. Someone, I think it's Roger Orr, said that the most beautiful line of code in C++ is the closing brace, because so much stuff happens just there. And that's actually true. So there's ways to get in trouble still in C++, like to return a temporary variable or a reference to something that is now dead and use it by accident. Even with very recent tools like string, you will hit those things sometimes. So we have an ongoing effort to reduce such cases because these are the ones that bite you. When you have a language where you don't manage memory yourself, you don't get those problems because as long as someone refers to an object, it's still alive. But there's costs to that, and nothing's free. So in C++, you do have to worry. We reason a lot about what happens when you copy an object, when you move it, when it goes out of existence. There are things that happen that you control in C++. It's the strength of the language, really, but it's tied to the way we think. We think about what assignment means. In other languages, you don't even control that, but we do, and we use it. But when you, as I said, when you have an object that returns temporary and then refers to that thing as dead, ugh. So advances in compiler technology help us find these bugs. Advances in the language help us find these bugs. I have a proposal in flight right now for a standard that lets functions say, when you pass an argument to me, after you've called me, you shouldn't be using it anymore because I might have done something to it. So it's actually something that I hope we'll get in C++ 29. Herb Sutter has a very big effort right now for lifetime stuff. We have a white paper in flight by Herb and a very nice guy called Jesper Asman. Again, I'm pronouncing his name right. Right person. They're working on something that reduces undefined behavior and such risks tied to lifetime. We're trying to narrow the scope of those bugs very strongly, lots of us working together at once, but we still have that in the language. What tools could you use? Now, we have sanitizers of all sorts. So sanitizers are programs that you can run on your code, either at runtime or at compile time, depending on what you do, and that will inform you that you're accessing something that is gone, or accessing an array out of bounds, or this or that. So there's tools for that are external to the compiler. We have an effort from Louis Dion, a fellow Québécois, again, a very bright guy, working on the client standard library called Standard Library Hardening. So they did measurements and they found that by enforcing some rules for, say, out-of-bounds access and stuff like that, they managed to get safer code with a very, very low cost, like 0.03%. That's very encouraging because we're very speed cautious in C++. So when the costs are very low, it's interesting. Otherwise, we probably wouldn't do it. So as you can see, lots of efforts there, both from the at once from the compiler side, from the language side, from the library side, and from external tools. So it's a concerted effort by many people to get the language safer.
Okay.
I think it's going great. Oh, and I should add profiles, because Bjarne has brought something called profiles to. You just recompile your code and you say, well, I really want my compiler to enforce those rules, and it will check bugs that you think are important in your code base. So you activate it if you want, or at least it's there by default, and you can deactivate it if you don't want it. Lots of my users will do that. But we have this. We have contracts coming into C++26, where you can mark preconditions of your functions, post-conditions of your functions, and some assertions, things that you think should hold at some point in your code, not as prose, but as code. You're saying this you should check. And depending on how you compile your code, either they will be checked, observed, ignored, different things can happen, but at least you wrote in the code what is supposed to be true when you come in the function, when you get the function, and at specific points inside. These are all ways to get your code better, safer, more correct. I don't think I'm answering correctly.
Yeah, brilliant. And great insights on like upcoming future, things that we are going to see soon. That was great.